Welcome back to the lab, folks. Today I have a little chip here. This chip here, it's a digital chip. It's a logic gate, and is one of my favorite of all time. And it's what it is 74LS86, which is a quad 2 input exclusive OR gate. And this is just such a powerful little chip. I mean, it allows you to produce some pretty sophisticated circuitry with implementation of relatively few gates because of its unique logic. Now I'm going to just introduce you to a couple of the interesting applications for it, but I'll link to a page below that will give you a lot more information about it, and I encourage you to go out and do a little bit more research on it. It's quite an interesting chip if you're into digital. Well, here's the symbol for it. It looks like a regular OR gate, except for it's got this little bracket on the back of it here. And this here is the truth table for it. So if both inputs are low, the output is low, just like a regular OR gate. One input is low, the other high. In either case, then the output is high, just like a regular OR gate. Now here's the big difference here. If both inputs are high, the output goes low again. So basically, it's doing a parity check or a comparison between. It's like a comparator. If the inputs are the same, the output is low. If the inputs are different, the output is high. So I did just hint at one of the applications that this chip was commonly used for, and that is parity checking. So you hardware parity checking done on a board where you have maybe 4 banks of memory. You need only 4 of these. Once you've calculated the parity of the memory, you feed the parity into the 74LS86, and it'll tell you whether your parity is odd or even. And you can go from there. So that's one of the applications of it. And another application is adding. So basically, if you take one of these and you put it parallel to it, a regular AND gate, what happens here is as soon as the two outputs go high, then this output will go to 1. So you'll get a 1 here. So if you have a 1 here, 1 here, you'll get a 0 here and a 1 here. So this here is your output and this is your carry. So basically what you're doing is you're adding these 2 bits together. So if they're both 0, you get 0, 0. So the 0, 0 carry. If one is high and the other is low, you'll get 1. So the sum of 1 and 0 is 1. And you get 1 on the output. And if both are high, you'll get 0 on the output and 1 carry. So that's what they call a half adder right there. And well, let's have a look at it. So we've had a look at the truth table here, and there's no point in looking at the rest of the data sheet on this because it's just a typical LS TTL device, and all the other pages are basically exactly the same as they would be for any other LS device. This is the important thing here. Now, this is also available in CMOS. I think that the 4030 and the 4070 are both exclusive OR gates, and off the top of my head I don't know the difference. I just remember that they were a thing, the 4030 and the 4070. And if you wanted, if you needed a circuit that could handle different voltages other than just 5 volts, then you would opt for the CMOS versions. Okay, so let's have a look here. Okay, I've got one set up here on our Heathkit Digital Design Experimenter. And we'll just run through that we can just run through that truth table here. And so we've got our data switches here. These are monitoring the data switches. The input's going into pins 1 and 2. So I've got the inputs going into pin 1 and 2. And I've got the output coming out of pin 3 here, going up to L4. So low, low, low. So we've got low, low, and low. So we got high, low is a high. Let's actually do that the way they have it on the data sheet. And that's exactly what we see. Now if we switch those around, we see we've also got a high. And then if they're both high, we get a low again. Nice and simple. Now, one of the applications I use it for a lot, and I thought this was a very, very handy thing. I did use it for as a comparator like this, of course. That's its main function. But one of the other functions I use it for, I'm just going to set up for that. So basically what I'm going to do is I'm going to take this input here and I'm going to put it on a clock up here. And let me hook up some oscilloscope probes to this. So we got this, we got the pink channel. Pink channel we'll put on the input. And the green channel we'll put on the output. I still want you to see the switch position here. So let me bring that down here. And I'll get the scope up on the screen for you. Okay, there we go. So we can see that the input and the output are in phase. What's happening on the input is happening on the output. Now, if we switch the other input on pin 1 to high, there you go. So basically what you have here is a programmable inverter. And that is a really nice, if you're ever designing a complex computer, with you want to interface it in a different way, you want to be able to change the interface on the fly, you want to be able to control something, this is really, really handy to be able to do this, to be able to change the properties of an inverter. And that's exactly what you can do with this. Now, this is another application I came up with for it back in college. If you look at this here, so if we've got the 7486 and the 7473 here, so the combination of the dual JK flip-flop and the 7476, you can build a rather unsophisticated but effective stepper motor controller. And all you need is a clock input to clock the motor at whatever speed you want, and a direction input to clock it either forward or backwards. And that all the logic for that can be implemented with just these two chips. Now this is the kind of, got 10 out of 10 on that. So this is the kind of waveform you get out of it. So it's not terribly sophisticated. It full steps this kind of motor, and there's no half steps available or micro steps or anything of that nature at all. So it's just a 4-phase, clocks through it, and then when you change the direction, which brings in the handy dandy programmable inverter capabilities of the LS86 here, by flipping the direction switch, then it counts the other way and you get the motor reversing. So that's a little project I came up with for college one time way back. I still have these stupid books, eh? Anyway, let's go up to the office now. I'll show you that page I'm going to link to down below, and quickly go through that as well. So there are other resources on the internet about the exclusive OR gate. Look it up if you want to play around with something really interesting in digital electronics. This is probably one of the most interesting little things you can play around with. Okay, here's that interesting document that I found. It's from the University of Technology in Iraq. They go through the basic theory of the gate, and then they go through a whole bunch of applications. So arithmetic operations, parity checker, that's one we discussed. And they give some examples of each circuit here. Well, not all of them. Controlled inverter, we showed you that one. Oh, this is an interesting one here, binary to gray and gray to binary conversion. So this could be handy if you only have access to binary information, but you want to simulate a rotary encoder, which are usually in gray code. This would be one way to do it. Or if you have a gray encoder and you want to take a binary output out of it, you can use an exclusive OR gate hooked up in this fashion. And it goes down through here. Combinational logic circuit minimization. I think I mentioned that too. That's, because of the sophistication of the gate, you can reduce the gate count in order to get your combinational logic sorted out. It's really handy in cases like that, as long as you can wrap your head around how it works. And the best way to do that is to actually play around with it and understand it. A digital comparator, I talked about that too. I mean, it is, as it stands, it is a single bit digital comparator. So that's why it works so well in parity checking and other things like that. Yeah, so and this little sheet here is set out as an experiment, so you could probably just sit down and follow it from beginning to end and get a little bit of a benefit from that. But you can feel free to look up on the internet some other examples. I think there's a good Wikipedia page on it as well. It goes into a little bit more detail. Of all the digital chips I had the opportunity to work with, this one seemed to capture my imagination the most. And it's always been one of my favorite chips. Anyway, thanks for coming out, guys. I'm still on the mend. You probably hear my voice today is a little bit suppressed, and my nose is sniffly, and so it looks like my COVID-19 is kind of morphed into a head cold. But I do have my chest is still rather heavy, and a little bit of discomfort in it still. So yeah, we're coming out of it. Thank you very much for your support, guys. I really appreciate it. We'll see you in the next video. Bye-bye.